matrix transformation, T of x equals A times x. A is the matrix 1, 0, 0, 0. So this transformation is a projection onto which axis? X1. Yeah. So let's see what happens. So it might be easier, it might be helpful if we answer number 2 before we answer number 1. So A is a 2 by 2, right? So if I'm going to do A times x, if A is 2 by 2, then x has to be 2 by 1. Yeah, it's a vector because of the arrow on top, which means it's got one column, and the inner dimensions have to match A. So x has to be a 2 by 1, right? And then the result of a 2 by 2 times a 2 by 1 should be a 2 by 1. Yeah, the 2's match, so you can multiply them, and the result is the outer dimensions 2 by 1. Okay, so my inputs are 2 by 1s, and the outputs are also 2 by 1s. So that means T goes from R2 to R2. The inputs live in R2, and the outputs live in R2. All right, so I know that my inputs and outputs go from R2 to R2. So if I multiply my A matrix 1, 0, 0, 1 times a random x1, x2, then my output should be 1 times x1 plus 0 times x2. That's my first one, x1. And then, oh, whoops, that's supposed to be a 0. And then 0. So that's going to be a projection onto the x1 axis. It takes any vector in R2, x1, x2, and it projects it onto the x1 axis. And is T 1 to 1? Correct. Wait. No, you're right. Why not? How do you know, Gabriella?
Because there's no pivot.
Yes. So for 1 to 1-ness, you're checking for pivots in every column, right? And does T map onto its codomain? No. And for mapping onto your codomain, you're looking for a pivot in every row. And what it means to map onto your codomain is that you can produce the entire codomain as outputs from your function or your transformation. But I can only produce things on the x-axis, right? I can't produce all of R2, my entire codomain, so it does not map onto its codomain. Okay, so the matrix of a linear transformation. So today we're going to look at the definitions of one-to-one and onto, and we're going to learn how to find the standard matrix of a linear transformation and how to use its columns to determine if the mapping is one-to-one and or onto. All right, so a couple of important definitions from the reading. A transformation is one-to-one, and remember, transformation is just a fancy form of the word function, right? Transformation is just a function. It's one-to-one if for each output in the range, there is a unique input in the domain that maps to it. Okay, so you probably learned about the term one-to-one in like a college algebra or pre-calc course, and you use the vertical line test, right, to see if there's more than one input that, the horizontal line test, to see if more than one input maps to the same output. Vertical is for a function. That's to test if it's a function. The horizontal tests for one-to-one. I'm sorry. So the horizontal line test tells you if there's more than one input that maps to the same output. That's probably when I went vertical. I was picturing two x values going to the same y value. Okay, so onto is a new word, but it still applies to your basic college algebra pre-calc functions. So we're going to do that in a minute, but it means a transformation maps onto its codomain if its range equals its codomain. If you can produce every element of the codomain as an output, then the transformation is onto every element in the codomain. Okay. So we're going to just look at some basic old-fashioned functions that go inputs are real numbers, outputs are real numbers, and determine if they're one-to-one or onto. So 3x minus 4, f of x equals 3x minus 4. So a quick sketch can help. So 3x minus 4 looks something like that, right? Is it one-to-one? Yes, it passes the horizontal line test. So there, for each y value, there's only one x value that maps to it. So this is one-to-one, one-to-one. And is it onto? So we know that its codomain is reals, right? Because all of these have outputs that are in the real numbers. Can you produce every single real number as an output of that function? No? Which one can't you build? Yes, right? Its range is all real numbers, negative infinity up to infinity, so it is onto. All right, f of x equals x squared. Looks like that, right? Is that one-to-one? No, it fails the horizontal line test, right? Because there are x values that more than one x value gets mapped to the same y value. So this is not one-to-one. Okay. And is it onto? Yes, y's. You can't get any negatives. Yeah, you can't produce you can't produce negative y values. So you can't get negative outputs from this function. So you can't produce all the real numbers as outputs of that function. So it's also not onto. Right, because the range of this guy is only 0 to infinity, whereas its codomain is all real numbers. Its range does not equal its codomain, so it's not onto. All right, f of x equals x cubed minus x squared. I think this looks something like that. Is that one-to-one? No, there's this little blip here where you can get where it fails the horizontal line test. Not one-to-one. But is it onto? Can I build every real number? Yes, the range of this guy is negative infinity to infinity. The y value, it covers all the y values as outputs. So it is onto, maps onto its codomain. And when you say a function is onto, that's shorthand for saying the function or the transformation maps onto its codomain. All right, f of x equals e to the x. Quick sketch. Looks like that. Is that guy one-to-one? Yes, passes the horizontal line test. Is it onto? No, you can't produce negative outputs. So it's one-to-one, but not onto. All right, so that's what the definitions mean in terms of concepts that we already know. We're also going to apply them to transformations that we use matrices for, where your inputs are vectors, your outputs are vectors. All right, so here I have a linear transformation. It goes from R2 to R3. I've got a little bit of information about it. I want to find its standard matrix and determine if it's one-to-one and or onto. Okay, so standard matrix A. So I need an A such that A times the vector 1, 0 gives me the vector 2, 6, 3. And when I take that A and I multiply it times the vector 0, 1, I get the vector 4, 0, 0. I'm looking for the AX, right? I'm looking for T of x equals AX. That's the A I'm looking for. That's what the standard matrix is. So let's do some analysis in terms of the dimensions. 1, 0 is a 2 by 1, right? Which means that A would have to be something by 2, right? 3 by 2 because the output is a 3 by 1. Yeah. So I may have to make the inner dimensions match and the outer dimensions are the result. 3 by 1. So A has to be a 3 by 2 matrix. So instead of writing A, I'm going to build an empty 3 by 2. 3 rows, 2 columns. So like, and then over here, same thing. I need a 3 row, 2 column matrix. And then I just have to figure out what to put in those 6 blanks so that when I multiply by 1, 0, I get 263, and when I multiply by 0, 1, I get 4, 0, 0. So if you remember the method of multiplying a matrix times a vector, take the first row times the vector, and that has to give you the 2, right? That has to give you the first entry of the result. So that means that this entry would have to be a 2, because no matter what's here, it's going to get multiplied by 0. And so when you add them together, you need the 2 from the first spot. So I don't have any information about what's going to go here, because whatever I multiply this second first row, second column, it's going to get multiplied by 0. So it doesn't really help. It's always going to end up zeroing out. But I'm just going to jump to the next row here, because the second row, oops, the second row times the vector should give me the second entry of the result. So if I have to put a 6 here to make that work, because whatever's in that second entry is going to get multiplied by 0. So you'd have 6 times 1 plus something times 0, so you get 6. And then in the third row, I'd have to have a 3 there. So 2, 6, 3, does that look like a familiar vector? Yeah, it was the given output, right? And that happened because I was multiplying by 1, 0, which is, we call that E1. It's the first column of the identity matrix in R2, 1, 0. Okay, so that's all I can get from this piece of information. Because of the 0, it doesn't allow me to glean any more information. But go to the other piece of information I have. And if you multiplied this first row times the vector 0, 1, it doesn't matter what's in this first spot. It's going to get multiplied by 0. But this second spot has to be a 4, so that you have the 4 times the 1 to give you the 4 as the output. And then in the second row, I'm going to have doesn't matter times 0, something times 1. I need that to come out to 0, so that has to be a 0, and that has to be a 0. And I get 4, 0, 0, which again, that was the vector that they gave me. And that worked out so nicely because they gave me 0, 1, which is the second column of the identity matrix in R2. We call that E2. Okay, so it turns out that my matrix A combined the information that I just gleaned there from those 2 pieces of information. It's 2, 6, 3, and 4, 0, 0. So there's my matrix A. That's called the standard matrix of the transformation. And if I row reduce it, I'm going to get 1, 0, 0, 0, 1, 0. That's going to help me answer the questions about one-to-one and onto. So we got to think about one-to-one. Let's think about onto first. Onto means that if I augmented with any B1, B2, B3 and row reduced, that this last row, it would be possible to have something in this spot that would make that inconsistent. Right? If you have a row of zeros, the augmented spot, if that is any number other than 0, we're now inconsistent, which means that there's a way to choose a B1, B2, B3 so that there's no solution, which means that it's not onto, right? You can't produce every possible vector in R3 because sometimes you'll get an inconsistent system. So the fact that there's no pivot in the third row, no pivot in row 3 before you augment, right, means that it's not onto. All right, so 1-to-1 means that when there is a solution, for every B1, B2, B3 that you can produce, is the X value that produces it unique. Is there only one X value that can produce that output? So if you have a pivot in every column, that means you have no free variables, right? So pivot in every column means that you have a unique solution. You only get more than one solution if you have a free variable and you get that infinite solution situation. So the fact that there's a pivot in every column means no free variables, which means there's a unique solution, which means that the function is 1-to-1. So the past few days now, the past few classes, we've been talking about answering various questions by looking at the pivots. Is there a pivot in every row? Is there a pivot in every column? And there are several questions you can answer by looking at where the pivots are. So on the next page, I'll let people finish writing this down, but on the next page, there's a super important summary about pivots and what questions they answer. Pivot in every row tells you lots of different things. It tells you that the transformation is onto. It tells you that the columns of A span Rm. It tells you that the matrix equation Ax equals B has a solution for all possible B. It tells you that every vector B in Rm in the codomain can be expressed as a linear combination of the columns of A. So there's many questions that you can answer just by looking at the matrix and saying, is there a pivot in every row? There's also lots of questions you can answer by checking if there's a pivot in every column. If there's a pivot in every column, then your transformation is 1-to-1. You also know that the columns of the matrix are linearly independent. And we know that when the matrix equation Ax equals B has a solution, it is unique. And we know that the matrix equation Ax equals 0 has only the trivial solution. That was the definition of linearly independent. So like keep that highlighted, put it on your note card. You know, you're going to use that to answer a lot of different kinds of questions. All right, we'll do one more together using this handy summary information to answer our questions. We have a linear transformation T. We want to find its standard matrix and determine if it's 1-to-1 and/or onto. All right, T goes from R5 to R3. So to find the standard matrix, I need to know where E1, E2, E3, E4, and E5 go. Those are just the columns of the identity matrix in R5. So I'm going to do T of E1. E1's a vector. It's the first column of the identity matrix in R5. So that means T of 1, 0, 0, 0, 0. So I'm just going to follow the rule. They said T of any 5-entry vector is a 3-entry vector where the first entry is x3 minus x4. So in this case, that would be 0 minus 0. The middle entry is 6 times x5, that's 6 times 0, and the third entry is 0. So T of E1 is just 0, 0, 0. T of E2. E2 is the second column of the identity matrix in R5. So this is T of 0, 1, 0, 0, 0. So you just keep moving the 1 entry down a spot. So E2, it's in the second position. All right, so this is a 3-entry output. x3 minus x4 is still 0. 6 times x5 is 0. And the third entry is always 0. T of E3. 0, 0, 1, 0, 0. Okay, so my rules for calculating the output. The first entry is x3 minus x4. x3 in this case is a 1. x4 is a 0. So 1 minus 0 is 1. 6 times x5, that's 6 times 0, which is 0. Third entry is always a 0. T of E3, E4. That's T of 0, 0, 0, 1, 0. x3 minus x4, that's 0 minus 1 is negative 1. 6 times x5 is 0. Third entry is always a 0. And then finally, T of E5, which is T of 1, 2, 3, 4, 1. So x3 minus x4 is 0. 6 times x5 is 6 now, because the x5 is a 1. And the third entry is always 0. So my standard matrix A for this transformation is just the columns that I produced as outputs of T of E1 up to T of E5. So T of E1 was 0, 0, 0. And E2. 0, 0, 0, 0, 0, 0. Then T of E3 is 1, 0, 0. T of E4 is negative 1, 0, 0. And T of E5 is 0, 6, 0. So it just happens that this matrix A is already in echelon form. It's not fully reduced echelon form, but it's each leading entry, it's in that triangular form. But I'll still row reduce it just to get in the habit. When you RREF this, since it's easy to do on a calculator, you might as well do it. 0, 0, 0, 0, 0, 0, 1, 0, 0, negative 1, 0, 0, and 0, 1, 0. All right, so we'll address 1 to 1 first. Is it 1 to 1? So let's go back up to our super important summary. Right, 1 to 1, we're looking for a pivot in every column. Is there a pivot in every column of this matrix? No. It's not 1 to 1. That means that for certain outputs, B1, B2, B3, you can create them with more than one input. And then onto, we're looking for a pivot in every row. Is there a pivot in every row? No. So that means there are elements from R3 that you cannot build as a linear combination of the columns of A.